Next we will look at what it means for a function to be continuous. So to talk about continuous, we'll first define what we mean by continuous. F, a function, is continuous at a point A if the limit equals the function evaluated at that point. And we're also going to assume that that limit is not infinity or negative infinity. So f is continuous if the limit equals the function evaluated at the point. Now, before illustrating this with a graph, I'm just going to make one remark. To check for continuity at a point, well, let's just say to check for continuity at a point A. That's too many A's. So I'll just say to check for continuity at A, we show that limit as x approaches A on the right equals the limit as x approaches A on the left, from the left, equals the function evaluated at A. And this is writing this out in more detail, but in the examples we see, we will be verifying this equation. And now, one way of understanding a function being continuous, well, the actual definition of continuous is not this. This is the example we use in calculus. The actual definition of continuous is actually quite complicated. Just like the actual definition of limit is quite complicated. But for calculus purposes, we'll leave it at this example. And one consequence of this example is that we can view continuous as a graph where, or continuous at a point, we can view as a graph where you don't have to lift your writing implement at that point. Now, to understand that a little more, let's look at a couple examples of functions that are not continuous at certain points. Well, let's look at one function that's not continuous at 3 points. Let's look at this example. So, example. This function illustrates 3 discontinuities. Let's say 3 kinds of discontinuities. So of course, function being continuous at a point, not being continuous at a point, we will say it is either not continuous or it has a discontinuity. So let's look at this example. And let's say this goes and then over like that. And let's label some numbers on this graph. Let's label 3, 5. That asymptote is at 7. And let's label this point up here as 2. Let's label that as 4. Let's label that as -6. So we don't have the same number showing up all over the place. Oh, I need another point. What am I doing? That point we'll say is 8. And this function, let's say that there's an arrow going over there like that. So right here, this function has 3 discontinuities. With that idea that a function is continuous if you can draw without lifting your writing implement, well, it's continuous, 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 continuous. Then you have to jump down here. So right here, it's not continuous at 3. So I'd like to have this entire board, so just pretend this function is still going. I guess if you were taking notes, you wrote that down. That part of the graph isn't going to be useful for the rest of this example, so I'm just going to get rid of it. So here, f, how do I want to phrase this? F is not continuous at colon 3. Let's just say 3. It's also not continuous with that writing implement idea at 5. It's also not continuous at 7. Now, why is it not continuous using limits? Remember, the definition of continuous said that the limit must equal the function at the point, and they must not be infinity. Well, what happens at 3? Well, the limit doesn't exist. So let's say, since limit as x approaches 3 from the left does not equal limit as x approaches 3 from the right. The limit on the left is 4. The limit on the right is -6. 4 and -6 are not the same number. Well, what happens at 5? Well, at 5, the limit is 2. Because on the left it's 2, on the right it's 2. But the function at 5 is 8. So this violates the second equal sign in that remark. So since, maybe I should have said up here, in that remark, this one violated the first equal sign. This one, not continuous at 5, since the limit as x approaches 5 of f does not equal f at 5. The limit is 2, f at 5 is 8. 2 and 8 are not the same. And here, this one is not continuous. We'll just say, since the limit as x approaches 7, you could choose either side of 7, or you could even say just 7, but all you need for this third type of violation is for the limit on one of the sides to be infinity. So I'm just going to say, since the limit on one side is infinity. You could say on the right, or you could say just in general that that limit is infinity. Now, we're going to define these three types of discontinuities. We're going to use words to describe them instead of just describing them with the limits. So here we have the three types of discontinuities defined formally. F has a jump discontinuity if the limit on the right does not equal the limit on the left. F has a removable discontinuity if the limit exists, but it's not the same as the function. And F has an infinite discontinuity at a point if the limit on either side of that point is a positive or a negative infinity. And here, this is a kind of an abusive notation. This notation doesn't actually exist with the positive negative there, but I'm going to use that to mean limit on the left or right is positive or negative infinity in that case. And in the previous example, the function had a jump discontinuity at 3, a removable discontinuity at 5, and an infinite discontinuity at 7. And in general, a jump discontinuity looks like, I guess they should be commas, it doesn't matter. A jump discontinuity looks like the function is doing something, and then it jumps somewhere else and continues on. A removable discontinuity is one where it just has a hole. The limit exists, but it isn't the function. And an infinite discontinuity, of course, is going to go off to infinity on one of the sides, or both sides. Or it could go off to negative infinity. Now, most of the functions we see are continuous, on their domains, of course. So let's record that as a theorem. So we can use this theorem in the future. Theorem. Polynomials. So like x squared plus 2x plus 3. Rational functions. So fractions of polynomials. Root functions. Trig functions. Inverse trig functions. Exponential functions. And logarithmic functions. Are all continuous on their domains. So if we have a function, it's almost guaranteed. If we have a function we can write down, it's basically guaranteed that it's going to be continuous on its domain, that we can write down algebraically, I should say. And one other important theorem regarding continuous is that if we take two continuous functions, so if f and g are continuous at a point, so we'll say at a and c is a constant, then the following are also continuous. F plus or minus g is continuous. F times g is continuous. F divided by g is continuous if g is not 0. And, I don't use Oxford commas, and c times f is continuous. I should say r, shouldn't I? If f and g are continuous at a and c is a constant, then f plus g, f minus g, f times g, f divided by g, and c times f are continuous at a. So if you take like an exponential function plus a logarithmic function, it's going to be continuous on its domain, and it's going to be continuous at given points. And I should capitalize that L since I capitalized everything else up there. So most of the functions we see are going to be continuous functions. All of the functions we see actually algebraically are going to be continuous functions. So one of the things we'll do, well, let's just do one example where we're using these theorems, and then let's do another type of example. So earlier in the semester, we found domains of functions, certain functions. Example, f of x equals x plus 1 over x minus 5. The domain of this function is everything except 5. So this is continuous on everything except 5. So it's continuous, negative infinity to 5, and 5 to infinity. Example, f of x equals root 16 minus x squared is continuous on its domain, which is -4 to 4. Algebraically, you can see that by solving this equation. By taking a square, you could use a sign chart. I would say not to. Numbers with squares less than 16 must be in this part of the number line. I kind of like to see that as just thinking of the numbers. Like a number out here, outside, like 4.2, 4.3 maybe, that squared is going to be larger than 16. Similarly, -4.2 squared is going to be larger than 16. But inside here, 3 squared, that works. 2 squared, that works. 1 squared, that works. -2 squared, that works. -3 squared, that works. And of course, 4 and -4 work because they equal. So this is continuous on its domain as well. This last function is actually, you know the graph of that function. How do I know what you know? I don't know. You've definitely seen it before. Positive square root. Keep that in mind. Radius 4. Positive square root means the top half only. So it is a semicircle. Centered at the origin, radius 4. As a side comment. But let's do another type of example with continuous functions. Example. Find the value a which makes f of x continuous. Everywhere. And I need to give you a function. Everywhere meaning -infinity to infinity. Let's define this function piecewise, meaning in pieces. So we're going to have, this function is going to be this, parabola type thing? Well, I guess it is just a parabola. If we're on that side of -4, and it's this line on that side of -4. So we want this function to be continuous everywhere. So the first observation we make is that this function is continuous. So first notice, this is just a parabola on that side of -4. This is just a line on that side of -4. They're both polynomials. So this is continuous on its domain. This is continuous on its domain. So overall, f is continuous already. continuous on everything except -4. What we have to do is ensure that this parabola and this line meet at -4. That drawing, they don't meet. We want to find the value a that guarantees they will meet at -4. But we first have that f is continuous on, well, everywhere else. That's not a u, that is a parenthesis, u. On -4, -infinity to -4, and 4 to infinity. Sorry, -4 to infinity. So all we have to do is check 4. So we force f to be continuous at negative 4. How do we force it to be continuous? Well, we force it to be continuous by letting the limit on the one side equal the limit on the other side. So let's write out those limits. Limit x approaches negative 4 on the left, since that function is first, equals this limit. Limit on the left, this function is defined like this on the left of 4. Left of negative 4. This function is defined like that. (4x squared minus 7). Well, we can now just substitute that in. 4 times 4, or negative 4 times negative 4 is 16. 4 times 16 is 64. 64 minus 7 is 57. Okay, great. Does that do what we want? No. We want this function to be continuous at negative 4, which means we want the limit on the left to be the limit on the right. So let's now take the limit on the right. The limit on the right of negative 4, well, the right of negative 4, this function is defined as 2ax plus 3. Now, we can substitute negative 4 in. Let x equal negative 4. And you get what? Negative 8a plus 3. What we want to do is force the limit on the left to be the same as the limit on the right. So let's force these to be equal. So, what do we have? 57. So, I'll just say then. Then 57 equals negative 8a plus 3. Are those the right numbers I have over here? Yeah, okay. I guess I didn't do this example in a few months. I didn't expect these numbers to this fraction to reduce, but I guess it does. Solve this for a, because we want a value a that'll force it to be continuous. Setting these two equal will force this function to be continuous at the last point that we need to be continuous at. Subtract 3. Divide by negative 8. Reduce the fraction, so those both have a 2. And now they have nothing else in common. So we'll say, so a equals 27/4, negative 27/4 makes f continuous. So all of these things we've done with continuous, whether it's defining the discontinuities or forcing functions to be continuous, all of it use the definition of continuous. So let's, oh, I had a page backwards. I forgot one result. Jeez. One of my pages got flipped around somehow. This should have been a theorem after that circle example. After the semicircle example. Sorry about that. So that example where we said that root 16 minus x squared is continuous on negative 4 to 4. Right after that, this theorem should have showed up and this example should have showed up. And then I should have done that, my bad. Theorem. If f is continuous at capital L and the limit as x approaches a of g of x equals L, then we can take the limit of a composition. Now, up to this point, we actually did not have limits of compositions other than limits of the other than the algebraic, the ones we could get from the algebraic limit laws. But here, this theorem, now that we have the word continuous, this theorem allows us to take limits of any composition. And how do we do that? Well, this theorem tells us we can do that by forcing this limit inside the composition. I'm going to write that under here. Equals f of limit x approaches a of g of x. But that inside equals L. So that equals f of L. In other words, we could do this, we could do limits with compositions through direct substitution. And as one example of this, let's look at this example. There's a good sentence as one example of this. Let's look at this example. Example, limit as x approaches pi over 2 of cosine of x minus pi over 2. Well, we can use this theorem to force this limit inside that function. That's what this theorem is doing. It's taking the limit and forcing it inside the function. So this equals cosine of the limit as x approaches pi over 2 of x minus pi over 2. Well, this we can use the algebraic limit laws on. So this is cosine of pi over 2 minus pi over 2. Using the algebraic limit laws there. And this equals, of course, cosine of 0, which equals, how do you do cosine of 0? Here's how I do it. X coordinate is cosine. Y coordinate is sine. That mistake showed up a handful of times in homework 1, confusing the x and y coordinates. That equals 1. So we did this, in essence, by a direct substitution. So everything we did with continuous functions actually is an immediate consequence of its definition using those limit equations. So to understand continuity, we really need to understand limits well.